Hi everyone, welcome back to Chem Story. Today, we're going to explore the physical properties of alkanes, especially their boiling and melting points. So what exactly affects these properties? How do things like molecular size or branching come into play? And why do some alkanes melt or boil at completely different temperatures than others? Understanding these trends can really help you predict how alkanes behave in different situations. Let's get into it. Alkanes tend to have lower boiling points than polar compounds of similar size. That's because the only intermolecular forces they've got are London dispersion forces, and those are pretty weak. But don't let that fool you. Even these weak forces can make a big difference when it comes to boiling points. As molecular weight increases, the boiling point goes up too. That's because larger molecules have more electrons, and that makes their dispersion forces stronger. On average, adding just one more carbon atom can raise the boiling point by about 20 to 30 degrees Celsius. Another key factor is molecular shape. The bigger the surface area, the stronger the intermolecular forces, and that means a higher boiling point. That's why straight-chain alkanes tend to have higher boiling points than their branched versions. More compact structures don't make as much contact with each other, so the forces between them are weaker, and their boiling points end up lower. Now let's put this trend to the test by comparing N-pentane, isopentane, and neopentane. N-pentane has a straight chain structure with a large surface area, so it stacks really well. That's why its boiling point is 36 degrees Celsius. Isopentane has a single branch, which means a little less surface contact, and its boiling point drops to 27.7 degrees Celsius. And neopentane? It's highly branched and almost spherical, so there's way less molecular contact. As a result, its boiling point drops all the way down to just 9.5 degrees Celsius. So the takeaway here is simple. The more branching, the weaker the intermolecular forces, and the lower the boiling point. That's exactly why highly branched molecules like neopentane evaporate so easily. Now let's talk about melting points. While boiling points are mostly affected by things like molecular weight and surface area, melting points work a little differently. They depend more on molecular size and symmetry. Just like with boiling points, larger alkanes usually have higher melting points because they have stronger intermolecular forces. But here's the key difference. Symmetry makes a big impact. Highly symmetrical molecules, especially ones with a more spherical shape, can pack together really neatly in a crystal lattice. That tight packing pulls the molecules closer together, which strengthens the intermolecular forces. So when it's time to melt, breaking apart that organized structure takes more energy, and that's what gives you a higher melting point. Let's compare the melting points of N-pentane and neopentane. The difference is huge. N-pentane has a linear shape, which doesn't pack very well in a solid lattice. That's why its melting point is as low as minus 130 degrees Celsius. Neopentane, on the other hand, is highly symmetrical, and that allows it to fit neatly into a crystal structure. Thanks to that tight packing, its melting point jumps up to minus 71 degrees Celsius. That's way higher than N-pentane, even though they both have the exact same molecular formula. This trend becomes even more dramatic when we compare cubane and N-octane. Cubane has almost perfect cubic symmetry, and because of that, its melting point is super high, 131 degrees Celsius. N-octane actually has a higher molecular weight, but it doesn't have that same symmetry, so its melting point drops all the way down to just minus 57 degrees Celsius. It's a clear example of how much symmetry can influence melting points. Now let's take a look at this graph to see how boiling and melting points change as the number of carbon atoms increases. The red curve shows the boiling points, and as you can see, they rise steadily as molecular weight goes up. The blue curve shows the melting points. They also increase, but with noticeable ups and downs. Here's something interesting. Even-numbered alkanes usually have slightly higher melting points than odd-numbered ones. Why is that? It comes down to packing. Even-numbered alkanes fit together more efficiently in a solid-state crystal structure, so the intermolecular forces between them are stronger. A great example of this is ethane, C2H6, an even-numbered alkane. Its melting point is actually higher than propane, even though ethane has a lower molecular weight. That better crystal packing really shows how much symmetry matters when it comes to melting points. So what can we take away from all this? Boiling points increase with molecular size, but they drop with branching because there's less molecular contact. Melting points are influenced by both molecular weight and symmetry, and highly symmetrical structures tend to have much higher melting points. And even-numbered alkanes usually melt at higher temperatures than odd-numbered ones, thanks to better packing in the solid state. Understanding these trends helps us predict how alkanes behave, whether we're using them as fuels, solvents, or industrial materials. Thanks for watching, and I'll see you next time.